All right, this first slide just reminds you of some important math rules. Feel free to copy those down into your notes if they are something that's unfamiliar to you. This first one is just the Pythagorean theorem. You may have seen it more as a squared plus b squared equals c squared. Those letters mean something in physics, A's and B's and C's, so I tend to think of it more just in terms of the parts of the triangle. Just a quick reminder that when you work with a right triangle, often denoted with this little square in the bottom, it's really important to be aware of what angle you are given or that you're trying to find, because everything is referenced to that angle. The hypotenuse is always the longest side, and it is typically at a diagonal in our class. The opposite side is the one that is directly across from the angle, and the adjacent is the one that is right next to the angle. It helps to form the angle itself along with the hypotenuse. We'll be going through each of these trig functions within some examples, but again, make sure you write them down if you need to. Also, remember that in your math class, you may have been given the mnemonic, the trick of SOHCAHTOA, and that helps us remember that sine is the opposite over the hypotenuse, cosine is the adjacent over the hypotenuse, and tangent is the opposite over the adjacent. So why do we need to worry about this kind of stuff in physics? In our class so far, when we've been asked to find the net force, our situations have been relatively simple in that the forces are to the left or the right or up or down. But what happens if that changes? That's what we're looking at in this video. What happens when things are at an angle? Before we get to that, just a quick review of how to find net force if things are along a line. We would think about the 30 newtons as pointing backwards and the 40 newtons as pointing forwards and subtract them or think of them as positives and negatives and get 10 newtons together. And then because the red force was bigger, then our net force points to the right. But if these same forces are not along the same line, if they point perpendicular to each other, we would need to be able to find the net force here too. And what we should see is that when you combine these two effects, if someone is pulling up and someone is pulling to the right on something, the object is going to get pulled sort of in this direction, up and to the right. So let's talk about how we would find that purple arrow, how we would find the amount of force and what exact direction it was pointing at. So the way that this second diagram is created is using what I like to call the head to tail method. And this method kind of ensures that you're going to get the arrow pointing the right way. Some people would just start with this picture on the left and try to make a triangle like this. But this is not the direction that the force, the net force, actually points. The net force needs to point somewhat up and somewhat to the right. So it is actually going to point in this sort of a direction. So it's best to go ahead and redraw the picture using this head to tail method. The head refers to the pointy part of an arrow and the tail refers to the back end. And so you would draw one of the arrows. I typically start with the one that's left or right, the X direction. And then at the head of that arrow, I start the tail of the next arrow. And by doing that, I will get the correct direction of my net force. It's this green arrow here. Notice that I've gone back to the beginning and kind of redone the picture, going to the end in one shot. So how do we find these different parts of the net force? How do we find the magnitude and the direction of that net force? That's what this video is about. Quick clarification, sometimes you'll hear me use the term net force, but sometimes I'll use resultant force. Those two terms are actually used interchangeably in this type of physics. They both refer to the overall amount of force that represents multiple forces together. They're both vectors, so they both have magnitudes and directions. but our direction is going to actually have two parts to it. We're going to have to state an angle, but also describe which way that angle is sort of pointed within the picture. So as we see here, the Pythagorean theorem is going to be helpful for finding the magnitude. Remember again that you may think of this as a squared plus b squared equals c squared. That's fine. But if we are trying to find out how big this hypotenuse is, we would use the Pythagorean theorem to do that. And so it would be 40 squared and 30 squared for our two sides. Take the square root of that result and you would get 50 newtons. But that's not the final story. We would also need to describe which way this force, this 50 newtons, is pointing. To do that, we would use the tangent function. Why would we choose a tangent function? Because the angle that we're given is here. We were given the value opposite that angle and the value adjacent to it. And so that 30 newtons would go on top and the 40 newtons would go on the bottom as we set up the tangent function. This is actually a good place to start, especially if you have a little bit of trouble with this, to start by thinking that theta is actually the inverse tangent, to sort of get that into your thinking right away. To undo the tangent, you would use your second key on your calculator to do the inverse tangent or the arctangent. This will come out to be 37 degrees. So now we can put all these things together. We used the Pythagorean theorem to find the value of the resultant force, and we used the tangent function to figure out the angle. And then we'd want to describe how that sort of points, how this green arrow points within space. So 50 newtons at 37 degrees, and we'd at this point have to say something like above right. It's kind of an awkward way of describing it. A lot of times we use compass directions, which we'll see in the next example. Feel free to draw this compass direction into your notes so that you can refer to it when you need to. If we're going to start with a force diagram that looks like this, we would want to first create a more appropriate triangle that really represents what's going on. Because again, if something is pointing, if there's a force to the right and a force that's down, the net force or the resultant force is going to point sort of in this direction. So we want to make sure that our diagram or our sketch matches that. I'm going to use the head to tail method again to represent this, starting with the 24 newtons, the one to the right, and then at the end of that, put in the 20 newtons. So things just sort of shift a little bit, and then I can start to see that there's this triangle being formed, and the hypotenuse of this triangle does point in the correct direction. Notice again, to draw this green arrow, I went back to the beginning and then went to the end. Okay, so it's not a complete like loop of arrows. This green or purple arrow represents like what you could replace everything else with, and the overall force would still be the same. So let's remember, how do we find the magnitude of that resultant force? We would use the Pythagorean theorem. These numbers don't come out quite as nice, so if you have trouble remembering or thinking about how do I round, a good rule is to keep a decimal point, a number past the decimal point. We also need to find the angle, so we need to pick the right trig function that will allow us to do that. Again, the trig function we want to use is the tangent, and you may want to have it already written in your notes as that theta is the inverse tangent, and make sure that you get the two sides in the right order. It doesn't matter so much with the Pythagorean theorem, but here it really does matter. The 20 is as far away from the angle as we can be. That's the opposite side. And the 24 is right next to the theta. And so that's going to be the adjacent. This should come out to be 40 degrees on your calculator. And I want to say the final result, it would be 31.2 newtons at 40 degrees south of east. Where did I get that south of east? Well, we can see that this angle, or this vector, I'm sorry, does point somewhere in the southeast quadrant. The main direction that I started with was the 24 newtons. So that's my reference. Compared to the east, I am like below that. I am south of east. So it's always going to match the, again, the quadrant that that net force should be in. The other skill we need with these sorts of situations where you have forces at an angle is how to take a force at an angle and break it apart into the components or the parts. It's just, components is just kind of a fancy word for parts. How to break that diagonal force into the components that are up, down, left, or right, or south, west, east, or north. To do that, we again want to picture a right triangle. So I want to picture a right triangle that includes that 50 degrees within the triangle. Okay, I need that for my work. And the 35 newtons, the diagonal force, is going to be your hypotenuse. Okay, so that's how that triangle should be set up. And then our two components, our two sides of the triangle, should also be arrows. They should have a direction to them. One of them is going to point to the west, and one of them is going to point to the south. Let's see what that looks like. So the one to the west I've labeled f sub x because it points along what we would normally call the x-axis, and then the one to the south I've labeled f sub y. This will help me organize my calculations. We would use the cosine function in order to determine the f sub x. How did I choose that? Well, I know the hypotenuse, and I'm looking for, at first, the side that is adjacent. And so I'm thinking SOHCAHTOA cosine gives me adjacent over hypotenuse. In this case, my unknown is on the top of the fraction. That's my f sub x. Our algebra would involve multiplying both sides by 35, and that's where the 22.5 newtons comes from. Then I would do something similar, but with the other side of the triangle, looking instead at the f sub y. And here I could switch to the sine function. The sine function involves the opposite side, which is what f sub y is. It's as far away from the angle as I can get. But I do the same sort of process. When you do these components, you generally will have cosine in one part of your calculations and sine in the other. These will get you the two sides of the triangle. It's just really important to keep track of which is which. So now I have my two values. I can finish this off. I can label that the 22.5 newtons is to the west and the 26.8 is to the south. Again, that just really comes from my picture, and it matches the way the information was originally given.